Hi everyone, my name is Kristoffer Nelson. I really enjoyed this course. I hope you all did too. For our final assignment, which was to predict the output energy from a combined cycle power plant using these environmental variables. Our first task was to describe the project topic section from above. Problem was described in the section above. We want to determine the machine learning approach and select an appropriate output metric to evaluate the performance of the model. The model inputs are temperature, ambient pressure, relative humidity, exhaust vacuum, and the outcome, is, as I said, is the net hourly electrical energy output. My main output metric for evaluation is going to be mean absolute error, or MAE. For this approach, a standard linear regression model is likely very sufficient. We may explore more refined regression models like ridge regression or lasso regression if needed. For the second task, determine which possible features we want to use in the model and identify different algorithms to consider. Out of the four metrics, intuitively, I'm thinking about two things. There's what I'm calling productivity metrics, and that is the exhaust vacuum and temperature. This to me indicates that the system is being more or less productive. And then you have these like what I'm calling environmental metrics, and it's the relative humidity and the ambient pressure. But I'm not sure that really indicates productivity or not. And so I'm ranking these. And if I was to stack rank this list, I would put exhaust vacuum above temperature. I selected relative humidity over ambient pressure in the stack ranking because relative humidity has much wider ranges, and it seems like that larger difference might help predict outcomes. Like I don't know, we'll see. That said, I decided to use the Google Cloud method of training as the option. I hadn't explored Google Cloud before and wanted to check that out. As I mentioned, algorithms to consider: linear regression, ridge regression, or lasso regression. You might remember this slide from a presentation early on, where these are both simple. All three of them are simple parametric algorithms. Task 3 was to split our data into test, evaluation, and performance for the final model. And then a fixed validation set, or using a cross-validation methodology. As I mentioned earlier, I utilize Google, and Google creates these splits for you automatically on default. Their automatic default is 80% of data is for training, 10% for validation, and 10% for testing. I decided to go with that. Task 4 was use your validation approach to compare at least two different models, which may be either different algorithms, the same algorithms with different combinations of features, or same algorithms and features for different variables and the hyperparameters. For among the models, you compare, select the model with the best performance for your validation set as your final model. I decided to go with two approaches. In Google, do I have a screenshot of this? Yeah, you can choose different ways to optimize your model and training. An RMSE training target, or an MAE training target. You can also do an RMSLE training target as well. So I decided to go with the RMSE, which will capture the more extreme values accurately. And with that, I decided to mix up the variables. And so in the first model, I'm going to use temperature and volume. In the second model, I'm going to use all of our features available. And so my first model, I'm sorry, not volume, but vacuum, exhaust vacuum, temperature and exhaust vacuum. And in my second model, I'm going to use exhaust temperature, relative humidity, and ambient pressure. So I ran them both models. Model one, oh, here I had that down here. Model one is going to run with the exhaust vacuum and temperature. Model two is going to run with all four. From our learning, we learned that MSE or RMSE penalizes severe errors more than May. MSE and RMSE is the most popular, and this is Google's default. And so, like I mentioned earlier, I went with that. You can see both of my models here. This is a screenshot of the models being trained. Version 2 on the left side of the screen, or my left side, the right side of the screen, where you maybe is using all four, and this on the other side is using just two. And so then we want to evaluate the performance of this after training. I'm going to go into this live demo here. So as you can see, version 2 using all four features in comparison to version 1. There's no label for version 1. I mean, this is interesting. What we see here is the mean absolute error is actually lower on the model that used just two features. We have better performance. The R hat squared is a little bit higher, a little bit better. Here it's 0.96 compared to 0.952. Here the May is 2.397. Here it is 2.577. The RMSE over here on the first model is 3.466, and it's 3.78 here. And then the MAPE, the mean absolute percentage error, is 53.53 here. And on the model using all four features, it's 0.57. So all in, the model using just temperature and exhaust vacuum volume performs better. Also interesting to note is the model with just two features, it was less training time overall, about 60% of the model using four features. And so this is a much more efficient model. We go into the evaluation. One thing that we notice here, we had an assumption earlier on, we ranked the vacuum volume higher, and what we actually see here is that temperature had much more of an impact on the overall importance of the outcome of the model. And so this is in model 1, where we just use the 2. If you look at model 2, where we used all four, you see a pretty big difference here. Temperature makes a big outsized impact over everything else. And so if we were to do this one more time, one thing we could consider would be training the model with just temperature and seeing what the outcome was for that. With that, I'm going to end here. Thank you all very much. It was a pleasure virtually taking this course with you.